Hey everyone, my name is Chris Norakis and I'm going to be presenting the edit distance algorithm. What this algorithm is, so it takes in two strings, an initial string and a target string. And what we're trying to do is transform initial into target with the minimum number of edits possible. So, for example, say we're trying to transform a book into the word back. One thing we could do is swap the second O with a C, the first O with an A, and then delete the leading A, and then we've done it. We've transformed a book into back. And that's said to have an edit distance of 3 because there's a minimum of 3 edits needed to do that transformation. Alright, so some overview on the problem. It's elite code hard, but it is solved in the book. And some applications or real world uses. It could be used for spell check in a phone or a word processor. So if a user misspells a word, you could take the edit distance between the misspelled word and say all the words in a dictionary and see what words are the most similar. Also, interestingly, online I saw that this could be used for comparing DNA sequences. So like long sequences of A and B. One metric you can use between two DNA sequences is the edit distance between both of them. Okay, so before I jump into the algorithms, I want to get some vocabulary out of the way. So what is an edit, or what are we allowed to do? Well, there's 3 things. So we can make an insertion. So consider the case where the initial string is AA, target string is AAB. One thing we're allowed to do is take the last letter in the target and add it to the end of the initial. So AA becomes AAB in this case. Next thing we're allowed to do is make a deletion. So if initials AAB targets AA, we're allowed to simply delete the last character of initial. And finally, we can make a substitution. So if initials AAB targets AAR, we're allowed to swap the last character of initial with the last character of target. So AAB becomes AAR. And now notice for each of these 3 edits, so we're always editing initial and we're always editing the last character of initial. So that's what we'll be working with in terms of the edits that we can make. Okay, now I'm going to show the first solution. We're calling this our intuitive solution. And it's here on the left. So the algorithm takes in string initial, string target. It's a recursive algorithm, so we're going to have some base cases. And if either the initial string or the target string are empty, we're simply going to return the other string's length. And that's because, say there's a case where initial is an empty string, target's ABC. We know that there's 3 edits required to go from the empty string to the target string, 3 insertions. Alright, next up we're going to compare the last character of initial with the last character of target. And that's for the case where, say, initial is ABC, target's DEC. What we're going to do in this case is simply recurse with A, B, and DE. So there's no edit required. We're just going to take each string prefix, that's just removing the last character from initial and target, and recurse on that. Finally, if the last characters of each string are not equal, we need to get into some of our edit cases. So the first case we're going to check is the substitution case. So if initial is ABC, target's DEF, we'd be making a recursive call with edit ABF and DEF. And then that counts as one edit operation. So a recursive call with the last character of initial swapped with the last character of target. Next up, we're going to check the insert case. So if initial is ABC, target's DEF, this would mean a recursive call to ABCF and DEF. This also counts as an edit operation. So the length of initial is going up by 1. We're simply taking the last character of target, adding that on to the end of initial. Alright, and finally the deletion case. So same setup, ABC, DEF for initial and target. In this case, you make a recursive call to AB and DEF, simply deleting the last character of initial. Then after making these 3 recursive calls, we're going to check to see what is the best. So this is a backtracking algorithm, and return that minimum edit distance. Alright, and that's it. That's the algorithm. But what I'm going to do next is kind of step through how this algorithm would work for a sample call, some of the mechanics of it. So say our initial string for this example is going to be BK, and the target string is going to be book. So stepping through our algorithm on this very first call, neither of the base cases hit because neither string is empty. But we do get a little lucky because the last characters are equal for this first call. So very first recursive call, we're just going to call with each prefix. Prefix of BK is B, prefix of book is boo. So now this is our next call, the edit distance between B and boo. Last characters are not equal, so now we need to check each one of our edit cases. So if we make a substitution, remember last character of target swaps with the last character of initial. So in this branch we have a recursive call between edit O and BOO. Insert, last character of target added to the end of initial, so this branch we're checking edit BO and BOO. And delete, simply delete the first character of initials. That's the edit distance between the empty string and boo. And now this is a base case call. So the edit distance between the empty string and boo, so that's 3. But it did take us 1 edit to get here. So adding those two things together gives us an edit distance of 4. So we have a answer, but we still need to step through these other 2 branches to see if we can do better. So going one step further, last characters are equal in this case, so that gives us the edit distance between the empty string and BO. Same logic here, so this is 2, but it took us 1 edit to get here. This has an edit distance of 3. Stepping down this branch, last characters are equal, so we can simply make a recursive call with the prefixes. So now we're checking the edit distance between B and BO. So we need to check each one of our cases again. I won't step through each of these cases this time, but we're making our same substitution, insert, and delete checks. This branch seems the most promising, inserting an O, or the last character of target, onto the end of initial. So taking this one step further. The last characters are equal in this case, so you can simply make a recursive call of prefixes, make another recursive call of prefixes. And finally, this gives us the edit distance between the empty string and the empty string, which this is 0. And it took us 2 edits to get to this case. The 2 insertions, inserting O and inserting O. And this edit distance of 2 is going to be the best that we get from any branch in this tree. So this is our answer. The answer is an edit distance of 2. And that's it. So this is kind of mechanically how this algorithm would work for an initial string and a target string. Okay, so the intuitive solution. I know it's a lot to look at in a short amount of time, but some of the pros that we found is it was easier for us to understand the solution than some of the others that we saw, just seeing exactly how the strings are edited. Cons, it uses a ton of memory. So if I run this test case, we're setting initial to intention, ABC, and target execution. The initial is an input string of length 12. We have some profiling set up, and this goes through roughly 11.3 million recursive calls, and it uses 152 megabytes of memory. So this is really inefficient, uses a ton of memory. So we can do better. So improving on the intuitive approach, the next implementation that we built, it's more of a algorithm-y example, we're calling it. Reason being that this solution uses global variables, it uses I's and J's, kind of similar to a lot of the pseudocode or the algorithms that we're seeing in our textbook. So I will show that really quick. This is our recurrence implementation. Now, same interface, there's a solve method that takes in an initial string and a target string. We're setting global variables initial and target. But what we're returning is this solve. This is a helper function, helper recursive function. And it's going to take in the initial string length and the target string length. So for initial ABCD, target ABC, this function would take in 4 and 3. And for the code itself, it looks similar, so same base cases. If we reach the end of one of the strings, simply return the other string's length. If the last characters are equal, simply recurse, taking the prefixes of each string. Where things got a little confusing, at least for me at least, are in these edit cases. So like I saw for the substitution case, we're making a recursive call with I-1 and J-1, and when I saw this, I was kind of just thinking why. But the reason being, if we go back to our intuitive solution, so say for the substitution case, remember we're swapping the last character of target with the last character of initial. So for the first recursive call, the lengths of each string stays the same. But on the very next call, the last characters are equal because we just set them to be equal. And we're immediately calling with the prefixes. So what this recursive solution is doing is kind of taking a shortcut and saying, I know after setting the last characters of these strings to be the same, we're just going to slice off the last characters anyway. So let's just decrement I and J right away to 1 without, kind of taking that step in the middle. And same with the insertion case. So for insertion, remember A, B, C, and D, E, F. We make a recursive call with A, B, C, F. So the length of initial at first goes up by 1. But then on this very next check on the last character, the length of initial is going to go back down by 1. So the end result of that, again, kind of taking a shortcut, length of I is going to stay the same, but the length of the target is going to go down by 1. And deletion is a simple case. We simply delete the last character of initial, so just decrement I by 1, J stays the same. And then same check, the min of these 3 branches. So this is the algorithm approach. It gets a little bit trickier to understand with the I's and J's, but it does have some pretty good improvements in terms of memory with the global variables. So memory doesn't even register. We're under a megabyte. Setting global variables initial and target helps a lot, but we are still at close to 7 million invocations, so it's still pretty slow. And how can we improve that? And the answer is dynamic programming. Now for the dynamic programming solution, for me this was one of the harder things in the course, just understanding dynamic programming, so I wanted to step through some of the how, in addition to just what the solution is. So the first step towards solving these dynamic programming problems is to solve the problem recursively. So dynamic programming really is just solving recursive problems backwards. And if you can't solve the problem to begin with, that's pretty hard to do. So most of the heavy lifting in coming up with a dynamic programming solution is to first solve the problem recursively. And up here I have a recurrence. This is really handy to have when solving these problems. It's the same thing I just shown in the editor, just kind of formalized a little bit in a handy cheat sheet format that we'll use. So once we have our recurrence, this is our recurrence here, next thing to do is to pick a data structure that can fit all potential calls to our recursive function. And what I mean by that is, so say initials horse, targets ROS, we need to establish our function call boundaries. So that initial function call, remember it's just the length of initial and the length of target. So it's going to be edit 5.3 in this case. And our final calls, edit 0.0, edit 0.1, edit 1.0, so all of our base case calls. So we know I is not going to go above 5, we know J is not going to go above 3. We know 0 is our min. There's actually 6 values in between 5 and 0. So what we need for the rows, or the i's, to save all those potential calls, is the length of initial plus 1. For the columns, same logic. Min is 0, max is 3. 4 values in between those 2 bounds. We need the length of target plus 1. And that's going to fit any potential call to edit ij. Alright, so we have our recurrence, we have our data structure that we know we need. The next thing we need to do is fill in that data structure, starting at the base cases and working toward the initial call. So stepping into our matrix here, so we have HORSE on the left, ROS on the top. we know our initial call is to edit distance 5, 3. So that's going to correspond to this cell on the matrix, just saying the 5th row, because I is our row, and the 3rd column because J is our column. So this cell corresponds to a call to edit distance 5, 3. So that's what we're trying to get to. All these dynamic programming problems, what we're trying to work to is the initial recursive call before we even started trying to solve the problem dynamically. Once we have that cell, we have our answer. But the problem is if we try to fill out that cell right off the bat, it's dependent on other cells that we don't know the answer to. So what we need to do is start with branches in our recurrence that don't have other dependencies. And those are our base case calls. So remember, every cell in the table is a function call. So this is a call to edit 0, 0. This is a call to edit 0, 1. And we can use our recurrence kind of as a cheat sheet to see what to fill out these cells with. So a call to edit 0, 1, stepping through what that would be, is I equal to 0? Yes, it is. In that case, the answer is J. So we know this cell would be 1. And similarly, for this cell, a call to edit 0, 2, is I 0? Yes, it is. Answer is J. Answer would be 2. So we have all of our base case calls here, and the next thing we need to do is to pick a cell, a little bit more complex cell. So say we choose this cell right here and try to fill it out. So this is a call to edit 1, 1. And now the call to edit 1, 1, stepping through this, is initial I equal to target J. The strings are 1 index, so is R equal to H? No, it's not. So we're in this branch. So now edit is the min between 1 row back, 1 column back, that's 0. Same row, 1 column back, that's 1. 1 column back, or 1 row back, same column, 1 plus 1. So the min of these three things plus 1, and that's going to be 1. Same thing with this cell, so is O equal to H? It's not, so we're looking at the min of these three cells plus 1, 2. Similarly, we can just go through this entire table filling out. This would be like edit 2, 1. Getting what each function call would be for each cell, using the recurrence to answer that, and then filling out the answer. And going through in whatever order we can. Finally get our answer of edit distance 5, 3, so we know the answer for the edit distance between these two strings is going to be 3. And that's it. So those are the 3 steps. Get a recurrence. It's really helpful to have that recurrence as a cheat sheet when filling out the table. Pick a data structure that can fit all potential calls. So find your min bound, max bound, every value in between. And then finally fill in that data structure, starting at the base cases. The initial recursive call is what we're trying to work towards and what our answer is going to be. Alright, now finally, I'm not going to show too much of the dynamic programming code because it's a lot to go over and we're short on time. But what I did want to show is the performance of the dynamic programming code for the same example we've been using. And it's pretty good. So remember, it took close to 11 million invocations for the intuitive solution. It takes 108 for dynamic programming, and memory doesn't even register. So this is a problem that can improve a lot with the dynamic programming solution. Alright, that's it. That's all I wanted to go over. I hope that everybody found the algorithm interesting and the explanations helpful. Thank you.